You are most welcome to this episode of our lessons in electrostatics. And in this episode, we are discussing the electric field. An electric field is the region within which an electric force due to a given charge is experienced. The region or the space around an electric charge where its electrostatic effect is experienced is what we are referring to as the electric field. Electric fields can be represented by electric field lines, that is diagrammatically. An electric field line is a path taken by a small positive charge when placed in an electric field. Like if I have a positive charge here and I bring close to it a small positive charge. Now this small positive charge will obviously be repelled or pushed away due to repulsion. Therefore, electric field lines that originate from a positive charge point away, showing us that they will repel in a nearby small positive charge. But if it was a negative charge and you bring close to it a small positive charge, this negative charge will attract the positive charge to it. That is why the electric field lines are drawn starting from the positive and terminating at a negative charge. These electric field lines are always short. Short because they're in a state of tension, short because the electrostatic force due to a charge is not indefinite, does not go on forever. There is a region where it's experienced and keeps fading off. So if you have them endlessly long, it means the electric field of a charge does not end. Now, electric field lines repel one another and therefore they do not cross. And the number of electric field lines, the density of electric field lines in a given region is proportional to the intensity of the strength of the electric field. So the more the electric field lines, the stronger that field that is being represented is. Also, that means when you have a large charge, a large magnitude of charge, you expect to have so many electric field lines starting or terminating at it. But if it is a small charge, then we expect to have scanty or few electric field lines that originate from it or that terminate on it if it is a negative charge. Then we have electric field patterns. And here we have taken interest in 6 of them. One is the electric field pattern of an isolated positive charge. As you can see, electric field lines are originating from it, pointing outwards. Then for the negative charge, electric field lines terminate at it. Then we have 2-point equal but opposite charges. You can see electric field lines originate from the positive charge and terminate at the negative charge. That is key in drawing the electric field patterns due to 2 equal but opposite charges. Roman numeral 4, we are looking at 2 parallel plates. One is negative and the other is positive. Electric field lines are originating from the positive charges on the positive plate and terminating at the negative charges on the negatively charged plate. The field around the middle of the region between the two plates is uniform. As you can see, the electric field lines are equally spaced. but they kind of warp outwards at the edges. Then we have the positive charges near, when they are placed near each other, they will repel, and in repelling, they form a neutral point in between them. The same thing applies to negative charges all placed near one another. This neutral point is the point in the electric field where the resultant electric force is zero. In other words, here electric field lines do not pass through or cross our neutral point at all, because at that point the electric fields have cancelled out and there is nothing like any electrostatic force being experienced there. The resultant force there is zero. What happens to the potential energy as two point charges of the same sign are brought together? When we bring these together, of course, since they are similar, the two charges will repel. So you have to do work against the repulsive forces between the two charges. So as you bring closer, work is done. Now this work, principle of conservation of energy, we can neither create nor destroy energy, but simply transform it from one form to another. So as you try to bring the two charges together forcefully against the repulsive force between them, the work which is done is stored as electric potential energy of the system where those charges exist. And the potential energy of the field between two like charges therefore increases when the charges are brought closer to one another. Conversely, if they are like charges and you try to separate them again, you are doing work against the attractive force between the two charges. And therefore, also as you take us apart two similar charges, the electric potential energy in the system where they are increases. And we have electric field intensity and electric field strength. Electric field intensity at any point in the electric field is the force experienced by a 1 coulomb of positive charge when placed in that electric field. I repeat, the electric field intensity or strength at a point in an electric field is the force that is experienced by a positive 1 coulomb of charge when placed in that at that point in the electric field. So since it is the force experienced by 1 coulomb charge, now in simple terms, the force per unit charge. The force per unit charge. So to get electric field intensity, we divide the force by charge. This force per unit charge. So electric field intensity E is F divided by H, where F is the electrostatic force. So since, if you recall from the previous episode, we said the electrostatic force between any 2 point charges, Q1, Q2, which are a distance r apart, is given by 1 out of 4 pi epsilon naught times that expression. That is, if I am taking it to be in air or in a vacuum. Now, here we are dealing with the 2 point charges. But now here they are saying is the force per unit charge, which means one of the two charges here can be taken to be a positive 1 coulomb. So if I put here a positive 1 coulomb of charge, 1 coulomb, and I put here a charge Q. So the force this charge will experience is the electric field intensity at that point where it is placed. So F is 1 out of 4 pi epsilon naught, then Q times 1 out of R squared. So it becomes, now this one is, since I have used the one here, so it now becomes our electric field intensity. And we have it as 1 over 4 pi epsilon naught Q over R squared. which you can easily work out as 9 times 10 power 9 Q out of R squared, as we have it here. So basically, since we are dividing the force by a charge, by a unit charge or by a charge, and the charge is a scalar quantity, so E, electric field intensity remains a vector quantity, and the procedures for working it out will be exactly the same as we are doing it for the electrostatic force. So we shall also be treating it as a vector and we look for the resultant electric field intensity at any point. The SI unit of electric field intensity is Newton per Coulomb or volt per meter. We have some examples here, around 5. We can go through them very fast. Question number 1, they're asking us to find the electric field intensity at a point P, which is 2 centimeters to the right of a negative 6 microcoulomb charge and 7 centimeters to the right of a 4 microcoulomb charge. We shall begin by working out the magnitude of the electric field intensity at P due to the charge at, let's say, the 4 microcoulomb charge. So E is given by 1 over 4 pi epsilon naught r squared. 1 out of 4 pi epsilon naught is 9 times 10 power 9. The charge in question here is 4 times 10 power negative 6. Still here we don't consider the sign of the charge. The sign of the charge only gives us the direction of the electric field intensity. So then the distance between the 4 microcoulomb charge and the charge P is 7 centimeters or 0.07. So when we substitute these values into the formula, we get 7.347 times 10 to the power negative 6 Newton per Coulomb. The direction, why is it being called towards the right? Because we said that if you have a positive charge here, if you place a positive charge at P and you have a positive 4 microcoulomb charge, what is the effect of the 4 microcoulomb charge on the positive 1 coulomb charge placed at P? The 4 microcoulomb charge will push it away, will repel it. That's why you are seeing the force, the electric field intensity due to the 4 microcoulomb charge is pointing towards the charge P, so it is pushing it away. We are not saying it is the force P exerts on the 4. It is the force the 4 microcoulomb charge is exerting on P. That's why it is pushing it away. Alternatively, you may not even draw it here, but you may put E4 here, showing that it is being pushed away by the 4 microcoulomb charge. Then we go to the electric field intensity due to the negative 6 microcoulomb charge. Still the same formula applies. We substitute the value of the charge, the magnitude, and the distance here is 2 centimeters or simply 0.02 meters. We substitute it into the formula for field electric field intensity and we get 1.35 times 10 power 8 Newton per Coulomb. And it is towards the left. Why towards the left? Because since this is a negative 6 microcoulomb charge, it is negative. If we place a positive 1 coulomb charge at P, it will be pulled towards the negative 6 microcoulomb charge because unlike charges do attract. So we have two forces, one is towards the left, the two electric field intensities, one is towards the left, the other one is towards the right. The one towards the left is a stronger one, so the net between the two is the bigger one minus the smaller one, and it will tend towards where the smaller one is. I advise us always If we can kindly, we can always make the one towards the right to be positive and the one towards the left to be negative. So the one towards the left is negative 1.35, the one towards the right is positive. Now when we add these two, negative plus a positive, we get a negative. Now the negative, after getting the negative, we can drop the negative in our final answer and say 1.2765 times 10 power 6 newton per coulomb towards the left. Towards the left. So it is always good to develop a general approach to different problems. Because always now the time division is bigger, may be taken across, especially when you have exponential figures like this. So what we have to do is ensure that left is negative, right is positive, then work out with that mentality in the final answer after adding the resultant force. It will show you which direction is actually taking. Number two, they're asking for electric field intensity at B. It is more or less the same as what we have so far done. So we have two charges at A 5 microcoulomb, at B negative 3 microcoulomb. The formula is still the same. Electric field intensity is charge over 4 pi epsilon naught r squared. The constant is 9 times 10 power 9. The charge at A is 5 microcoulomb. So when we substitute the distance also is 0.1 from B, when we substitute, we get 4.5 times 10 power negative 6 Newton per coulomb towards the right. Why towards the right? Because we are putting a positive 1 microcoulomb charge, a positive 1 coulomb charge at B, so it will receive a repulsive force. A will push it away, so it will be pushed towards the right. So the effect of charge A on B is that it will push it away and B moves towards the right. That's why the electric field intensity at B has been gotten to be towards the right. Then the charge C is negative. So what happens to B when it comes a small positive charge coming near a negative 3 microcoulomb charge? That small positive charge will be pulled towards the negative charge. So that's why you're seeing electric field intensity due to the charge at B is pointing towards the right. So they are both positive since they are both pointing towards the right. So to get the resultant electric field intensity E, here, always endeavor to respect the units of these quantities. Shall get 15.3 times 10 power 6 Newton per coulomb towards the right. Towards the right. Question number 3. This time we have a triangle. The triangle ABC with 2-point charges, one of 5 microcoulomb, the other of negative 3 microcoulomb, placed at corners A and B, and we're supposed to find the electric field intensity at C. The minor correction here is supposed to be at C. Observations that we should always make on these triangles. First of all, we should establish the angles of interest in this triangle, especially the angles along which we expect to resolve forces or electric field intensities or any vectors. So since our triangle is equilateral, even if we don't work out this, clearly we see that this triangle has 3 equal sides, then therefore it has equal angles. And since the angles are left 180 degrees, 180 divided by 3, sharing 180 equally, each interior angle is 60 degrees. And however, you can still do it the other way around by dropping an altitude from C downwards. You will divide the lower side into 10, then cos inverse of 10 over 20, you get 60 degrees, and can work. Now, we now go into the physics. We're done with geometry of the figure. We now go into the physics around the problem. If you place a positive 1 coulomb charge At C, at C, the charge at A is positive, so it will push it away. So you see, electric field intensity due to the 5 microcoulomb charge is pointing away. Then the charge at B is negative, so it will try to pull the charge that you have placed at C. So you see the electric field intensity due to B is pointing towards the charge B because it's an attraction and like charges attract. Now if you work out the magnitudes of electric field intensity at A, electric field intensity at B using the formula that we have already seen, electric field intensity is Q over 4 pi epsilon naught R squared. If you substitute the corresponding values for the charge at A, you get electric field intensity at A is 1.125 times 10 to the power 6 Newton per Coulomb. If you substitute the details of charge B, the charge and the density is from C, you get electric field intensity due to B as 6.75 times 10 to the power 5 newtons per coulomb. Now, having got the magnitude, remember we're dealing with a vector quantity, so we have to go back and resolve these electric field intensities so that we deal with components. We start with the one for EA. We have to first, because we must break it down into horizontal and vertical intensities as we are doing it for the forces. So we still draw a horizontal line here. Then the angles are corresponding. So if this angle is 60, even this angle is 60. If this angle is 60 degrees, then this angle is also 60 degrees. These two are alt and these other two are corresponding. Now, having seen that one, our EA will have two components. The one next to the angle will be EA cos of 60, and therefore the other one would be EA sine of 60. Then for EB, it will also still have two components. The one next to the angle will be EB, the cos of 60. The one, yeah, that means the other one remaining will be pointing downwards and will be EB, the sine of 60. Therefore, in vector form, EA, EA, EA has a positive horizontal component, which is EA, the cos of 60, which is here. It is pointing towards the right. Then it has a positive y component, which is EA sine of 60. Don't always forget to put the symbols of degrees because they might be mistaken for radians or some other quantities which are not angles. Then for EB has two components. One is first, EB has the horizontal facing towards the right, so it is positive. EB 6.75 times 10 to the power 5 cos of 60. Then the other one is the vertical one is facing downwards and it is negative 6.65, 6.75 times 10 to the power 5 sin 60. The negative shows that it's pointing downwards. When you work those ones out, you get two positive components of the result at electric field in vector form, which will be subject to a triangle vectors or rectangle vectors to get the magnitude and the direction of the resultant electric field intensity. Still, my advice and the simpler method of doing this is getting your ruler and drawing a rectangle. After drawing the rectangle, you consider the horizontal component of the electric field intensity or of any vector. In this case, it is positive, so it is facing towards the right. You put it on both sides. Then one which is the vertical component also is positive, so we put them two also. EY and EY. This is EX, this is Newton per Coulomb. Newton per Coulomb. This is EX, and this is EY. Then you look for the corner where two arrows originate, and the corner is here. You draw your resultant electric field intensity, the angle it makes with the horizontal. Let me call it alpha. So, as we are doing it for the electrostatic force, we look for the resultant magnitude using Pythagoras theorem. Then we look for the angle using the tangent, and we conclude that therefore the electric field that results is 9.81 times 10 power 5 Newton per coulomb at 23.4 degrees to the horizontal. Number four, for question number four, we have 2-point charges and B of charges 0.10 microcoulomb, 0.05 microcoulomb respectively, placed 8 centimeters apart as shown below. We are asked to find, there's no question here, but we are supposed to find the resultant electric field intensity at C. This time the difference comes only at the point that the two charges are all positive, that is 1, 2, then our triangle is no longer quadrilateral. This time it is isosceles, and therefore we shall have to find it using trigonometry, find the required angles using trigonometry. So dropping an altitude from here, the direction to 244, then we shall use cos inverse 4/5 to be our angle theta of interest that we have marked here, because we shall need it in resolving forces. The other parts remain the same as it was for the example that we have just done. Lastly, we have a rectangle PQRS with 3 charges at PQR, and we are required to find the resultant electric field strength at S. The word strength and intensity can be used interchangeably, so don't be bedazzled when you meet them being used in terms. Now, let us place a positive 1 coulomb charge at the point of interest S, and we observe how the 3 charges will treat that positive charge. The one at R is positive, so it will repel it off. So you see ER is pointing upwards. It is worked out as 1.44 times 10 power 4 Newton per coulomb. I know now you're familiar with that conversion. ER is 3.3 times 10 power 4 Newton per coulomb and is facing upwards. The charge at P is negative. The charge at P is negative. So since the charge at P is negative, it will attract the positive one that we have placed at S. This was an error. So we expect this positive charge to be attracted towards the charge at P. So that is EP. So EP is facing backwards or towards the left. Then we also have the charge at Q. Now this one we have to first establish the distance between Q and S by seeing that it is the longest side of the triangle QSR. So using Pythagoras theorem, it is discovered to be 5 centimeters. Please don't just watch these videos. Be pausing the video and working out these things. I'm doing it in the interest of time, but for you, and in favoring the length of the video, for you can actually do it step by step. Pause the video and talk about something, pause the video, analyze it, write it down in your notebook for easy reference and understanding. Physics is understood best when we involve ourselves in it. So, even the angle theta may be the angle of interest because we shall need to resolve this electric field intensity into 2 components. This component down here this one and that one. So which correspondingly when you put here, you'll have two components. After working out EQ, it is a repulsive force because Q is positive, this pushing away the other one. Now this angle theta is the same as the angle we have here. So we shall have two components. One next to the angle will be EQ, the cos of theta has been got already at the 6.9. So we'll have EQ, the sine of theta. Then later on, we shall decompose all the electric field intensities into their components so to get the resultant vector that is required. So when it comes to solution, we shall look at those which are entirely horizontal. Entirely horizontal, it was the EP but negative. So EP is negative and is entirely horizontal. That's why you see here it has a zero vertical intensity. Then ER is entirely vertical and is pointing upwards. It is positive here. It has a zero horizontal component, but EQ has two components. Each with sin theta is upward and positive is here. Then EQ cos of theta is horizontal and pointing towards the right, so it is positive and is here. So when you work out that one, you will get the vector form, of course, of the electric field intensity first. Then you look for the resultant using Pythagoras theorem and the angle concerned. And the angle concerned also is got. So when you work out these ones, here you come here. So the distortion somehow from here, you come here now. From here you will come there. So when you add these ones up, you get these two. X is negative and Y is positive. But always don't forget the Newton per coulomb. And don't forget the degrees on the angles when working. So this time we have horizontal is negative and vertical is positive. Horizontal negative facing backwards, vertical is positive facing upwards. So our aim is to get E and the angle alpha. Still, if you want to use the other trick I told you of visual drawing this rectangle forces, drawing a rectangle, horizontal is negative, EX, vertical is positive, EY. So there is a corner which has two arrows coming from it. It's this down corner here. So we draw starting from there to get our result. Of course, you have to use a ruler. That is E. Then the angle it makes with the horizontal, that is theta. Alpha, sorry, in this case. As you have already used the alpha, theta up there. Alpha, so you get the angle alpha by inverse tan, and you get the modulus of the magnitude using Pythagoras theorem, and you conclude as required. We have an exercise here that we can try in order for us to consolidate what we have so far looked at. That is question number 1, question number 2, question number 3. You can easily pause the video and work it out. Question number 4 is also there. Kindly pause the video and try those questions out. They're very important. Then we have question number 5. And we have question number 6. Question number 5 is there. Question number 6 is also there. Kindly pause the video and try those questions up to question number 7. Let's also talk briefly about electrostatics shielding or screening. Screening or shielding is an application of an electrical neutral space in the neighborhood of an electric field, however strong the external field is. So we want to create a safe space, a small region where in that region there is electrical neutrality. In other words, there is no electric activity taking place. The resultant electric field intensity at any point inside that area is zero. Even if it is in a very strong electric field, you can create it by electrostatic screening or shielding. How do we do it? You get a hollow contact, what you call a Faraday cage, and surround that charge that you want to shield, or that charge object which you want to shield with that cage, which is earthed. So you earth the cage or the conductor and surround the charge or the conductor in equation that you want to protect. You put in that cage. So the charged body is enclosed in a hollow conductor which is earthed. That is the Faraday cage. Now, this charge which you have enclosed will induce an equal but opposite charge on the inside of the conductor and will repel the similar charges through the earth into the ground. Now, the electric field outside will not affect the charged body at all, and therefore you would have electrically shielded our conductor. Don't forget that charge resides on the outside of the conductor. So we shall not have any electric charges on the inside space, but we shall have just induced an opposite charge on the walls of the Faraday cage that we are using to screen our given charged body. Then we have electric flux. Electric flux is the product of electric field strength at any point and the area normal to the field. You have you have electric field strength is shown by electric field lines. So if I have electric field due to a charge, and electric field lines are being shown by this. So if I have an area normal to this one, the electric flux passing through this area A, the electric flux phi will be that area normal to the electric field, like the electric field intensity at that point. So electric flux is the product of the electric field intensity or strength at any point and the area normal to that electric field at that point. So obviously the electric flux has units. This electric field intensity is volts per meter. Multiplying it by meter squared, so it becomes voltmeter. It's either voltmeter or you can call it per coulomb per square meter. Newton per coulomb square meter. The units of electric flux. Now, total electric flux, we want us to consider, here we're trying to drive out Gauss's law. We want us to consider a sphere, but now here it looks like a circle, but it's a sphere, so it is all round. A sphere of radius r. Now this sphere is given a charge q. So on its surface it has a charge q. Now I want to look at the electric field at any point from this sphere. It is given by E is q over 4 pi epsilon naught r squared. Now electric flux through any spherical surface of radius r is given by AE. But now a spherical surface has an area of 4 pi 4 pi r squared, that is the surface area of a spherical surface of radius r, and then the electric field intensity through that point also given by q of 4 pi epsilon r squared, where epsilon is the permittivity of the medium in the sphere. If it's, of course, if it is air, by good approximation, or if it is a vacuum, it is epsilon naught. So when you multiply something also, and you end with charge q out of r squared, you charge q out of epsilon, which is Gauss's law of electrostatics. Now, this Gauss's law states that the total electric flux passing normally through a closed surface, no matter the shape, is always a constant and is given by charge q over the permittivity of that space, of the medium in that space or region enclosed by that surface. Now, electric field intensity due to a hollow conductor. Now, as we have seen, due to a hollow charged sphere, charged conductor. Now, outside the sphere, you are moving outwards from the sphere, and as you move a distance r from the sphere, so we assume that all the charge is at the center of the sphere. So as you move a distance r radius from the center of the sphere, the electric field intensity E is a q over 4 pi epsilon naught r squared, as the formula is, for a distance r from a charge. And since 1 over 4 pi epsilon naught is a constant, so we can say that E is equal to k over r squared. Because even q, the charge we are talking about, is not varying. So q over 4 pi epsilon naught is a constant. So if we take it to be a constant of proportionality, we shall have E, when we remove it, we get the symbol proportionality 1 over r squared, which means the electric field intensity varies inversely as the square of the distance of separation outside the sphere. Now, since as we saw in Faraday's ice-pair experiments that charge fully resides on the outside of the sphere, there is no charge inside the sphere, and therefore the electric field intensity inside the hollow charged sphere is 0. So this comes to our graph here, our graph of electric field intensity against distance. Inside the sphere, electric field intensity is 0, as what you're seeing laying down at 0. But as you move out beyond the surface of the sphere, the hollow charged sphere, now it is varying inversely as the square of r. So there is that abrupt fall or rise from 0, and then it keeps on reducing because it is inversely proportional to the square of the distance from the sphere. This marks the end of our episode about electric fields, electric field intensity. In our next episode, we shall be discussing electric potential and electric potential difference. But don't forget to subscribe to our channel to keep this work moving, and share to our friends. And if you have been impacted by this video or any of the similar videos, kindly subscribe to our channel so that we grow this content. Thank you.